Hello and welcome. Tonight, we're setting sail into the farthest horizons of imagination to glimpse civilizations that may one day rise from the seeds we're planting now. Worlds lit by artificial suns, minds woven together across galaxies, and societies so advanced that our own age might seem like the first flicker of dawn. This is the story of future civilizations. How we might grow beyond Earth, what technologies could shape our destiny, and the strange, beautiful possibilities waiting for those who endure the tides of time. So if you're ready to unwind, close your eyes to the noise of the present and drift forward into centuries yet to come. Make sure to subscribe and turn on notifications so you'll never miss another voyage into the boundless realms of thought. Now, let's begin. Chapter 1: The Measure of a Civilization. Imagine, for a moment, standing far above our galaxy, far enough that the whole Milky Way hangs before you like a swirling, luminous island adrift in a black cosmic sea. Down there, on one tiny speck orbiting one unremarkable star, life has reached a remarkable point. It has invented stories, mathematics, music, and machines. It has split atoms, mapped genomes, and peered back to the birth of the universe itself. But from a galactic vantage point, our species is still very young, perhaps no older than a child taking its first uncertain steps. This is where the idea of measuring a civilization begins, not in terms of its morality or art or culture. Those are impossible to reduce to a single scale, but in terms of its capacity to harness and direct energy. In 1964, Soviet astrophysicist Nikolai Kardashev proposed a now famous framework for categorizing civilizations, known as the Kardashev scale. It's an idea that has endured because it gives us a cosmic yardstick, a way to place ourselves on a spectrum that stretches from the present day into unimaginable futures. The Kardashev scale has three main categories, though it can be extended to more. A Type 1, civilization, sometimes called a planetary civilization, can use and store all of the energy available on its home planet. That means capturing every bit of solar energy that reaches the ground, tapping geothermal heat from the core, channeling winds, tides, and rivers without waste, and using all these resources sustainably. By Kardashev's measure, Earth is not yet at Type 1. Various estimates place us at around 0.72, which might sound encouraging until you realize that, at our current rate, it could take another 100 to 200 years to reach Type 1 status. A Type 2 civilization can harness the full energy output of its star. This isn't about covering a few deserts with solar panels. It means engineering structures on a scale so vast they encircle the star itself, capturing its light before it escapes into space. This is where concepts like Dyson spheres come into play. Megastructures that could turn a star into a power station capable of running colossal computational systems, terraforming planets, or sustaining vast populations. A Type 3 civilization goes even further, commanding the energy of an entire galaxy. They might build stellar-scale machines, manipulate black holes, and traverse interstellar distances as easily as we travel between cities. From our perspective, such civilizations would appear as cosmic forces, altering the structure of galaxies, their engineering written into the stars themselves. Kardashev's scale is not without its limits. It focuses purely on energy consumption, and while energy is essential for any civilization, it doesn't capture the subtleties of social complexity, wisdom, or sustainability. After all, a reckless Type 2 society that burns through its star's resources without thought might collapse long before a gentler, more modest culture that lives within its means. Still, the scale gives us a kind of ladder, and perhaps more importantly, it forces us to look upward and forward. But before we climb that ladder, it's worth reflecting on where we are. Right now, humanity's energy use is vast in our own terms, roughly 18 terawatts globally, but it's a whisper against the power raining down from the sun. Every second, our star outputs about 386 yottawatts. That's 386 trillion watts. Enough to power our civilization for millions of years in an instant. Yet we catch only a fraction of 1% of that gift, and we often squander even that through inefficiency and waste. Becoming a Type 1 civilization is more than an engineering project. It's a test of global unity. It means stabilizing our climate, managing resources without exhausting them, and designing systems that can handle energy at planetary scales without destabilizing the very biosphere we depend on. It also means political coordination, because energy infrastructure that spans continents cannot be the exclusive property of any one nation. Reaching Type 1 is as much about learning to cooperate as it is about building bigger machines. This is where the Kardashev scale becomes more than an abstract chart. It challenges us with a choice. We can stay at our current level, vulnerable to self-inflicted collapse, or we can take the long, deliberate climb toward greater capability and stability. And in that climb, something interesting happens. We start thinking like a species, not a collection of rival tribes. The technologies we'll need to reach Type 1 are not science fiction. Large-scale solar collectors, geothermal grids, advanced wind and tidal farms, high-efficiency energy storage, and smart global distribution networks. Many of these exist in some form today. The challenge is scaling them, integrating them, and transforming them into a system that can deliver energy abundance without environmental ruin. But as we contemplate those systems, we inevitably imagine what lies beyond. A Type 1 civilization might be a planetary gardener, tending its world as a balanced ecosystem. A Type 2 civilization might be an architect of star systems, moving planets into more favorable orbits, constructing vast rings or spheres around suns, or using controlled fusion reactions on a scale we can barely picture. A Type 3 might weave civilizations together across thousands of light years, their communication carried not by radio waves, but by manipulated space-time itself. There's another reason Kardashev's vision matters. It gives us a framework for imagining other civilizations. Astronomers searching for extraterrestrial intelligence often consider how a Type 2 or Type 3 might appear from Earth. A Dyson sphere, for instance, wouldn't emit much visible light. It would glow in infrared as it radiated waste heat. A civilization manipulating stars might create patterns or motions that no natural process could mimic. If we ever detect such signs, it could mean we're not the only climbers on this cosmic ladder. Still, there's an important caution. Power is not the same as wisdom. We can imagine a species racing to Type 2 status, only to extinguish itself in war, accident, or environmental collapse. The Kardashev scale doesn't account for moral growth, empathy, or restraint, qualities that might be just as important for long-term survival as the ability to tap more watts. And yet, perhaps that's the beauty of it. The scale gives us a physical challenge to increase our energy mastery, while history and experience remind us that the cultural challenge is just as steep. To reach the higher rungs, we must not only learn to gather the light of the sun, we must learn to use that light wisely. For now, we remain a Type 0 species, reliant on fossil fuels that formed millions of years ago, vulnerable to asteroid impacts, pandemics, and our own political divisions. But the ladder is there, and the first step to become a true planetary civilization is within sight if we choose to take it. The transition will not be a straight climb. It will be marked by leaps, breakthroughs in fusion energy, global cooperation on climate, the spread of autonomous energy systems, and perhaps even the first stirrings of a space-based economy. Each step upward will change not only our technical abilities, but the way we see ourselves. The day we reach Type 1 will be the day we know, truly know, that we have become a species with a shared fate and a shared future. That awareness may be the most valuable power of all. For beyond the numbers, beyond the megawatts and the engineering marvels, the Kardashev scale whispers a question. What kind of civilization do we want to be when we arrive? Because in the end, the measure of a civilization is not just how much energy it can command, but how far its vision can reach. And ours is just beginning to stretch beyond the thin shell of atmosphere into the deep, star-strewn dark, toward the civilizations that may one day blaze across the sky as beacons of what is possible. In the next chapter, we'll step beyond our own world entirely to explore the first great leap beyond Type 1, the construction of vast stellar engines and the dream of building a Dyson sphere. It is here that engineering ambition meets cosmic scale, and where humanity's first steps toward Type 2 might be taken. Chapter 2, Capturing the Sun. If the leap from Type 0 to Type 1 feels vast, the leap from Type 1 to Type 2 is almost dizzying. A Type 1 civilization commands the resources of an entire planet. A Type 2 civilization commands the full power of its star. The difference is not simply in scale, it is a change in the very fabric of what a civilization can do, how it thinks, and how it sees itself in relation to the cosmos. To appreciate the challenge, let's start with the raw numbers. The sun outputs about 386 yottawatts of energy every second. That's 386 trillion watts, a figure so large it resists intuition. By comparison, all of humanity's annual energy consumption amounts to less than what the sun emits in a single second. Even the sunlight that actually reaches Earth's surface, a tiny fraction of the total, dwarfs what we currently use. To reach Type 2, we'd need to find a way to collect nearly all of that energy before it radiates uselessly into space. And that means building structures and systems on a scale that, today, feels almost mythic. In 1960, physicist Freeman Dyson proposed an idea that has since become shorthand for the ambitions of advanced civilizations, the Dyson sphere. His thought experiment began with a simple question. If a civilization's energy needs grew far beyond the capacity of its home planet, where could it turn? The answer, Dyson suggested, was obvious: to its star. Dyson didn't mean a solid, shell-like sphere surrounding the sun. That would be mechanically unstable and probably impossible with any material we know. Instead, he imagined a vast swarm of satellites, each fitted with solar collectors, orbiting in a dense cloud around the star. Together, these satellites would capture most of the star's output, transmitting it as energy beams, perhaps microwaves or lasers, to receivers elsewhere in the solar system. This idea, now often called a Dyson swarm, is more plausible than a rigid sphere and allows for incremental construction. A civilization could start small, adding new collectors over decades or centuries, gradually increasing its energy capture. The result would be a slow but steady transformation, with the star gradually dimming in visible light while glowing more brightly in the infrared, as waste heat radiated from the collectors. The scale of the engineering challenge is difficult to overstate. A single solar collector large enough to make a noticeable difference might span kilometers. Millions, even billions, of such units would be needed. The material requirements alone exceed what Earth's crust could easily supply, which is why some futurists imagine dismantling small planets, moons, or asteroids to provide raw materials. Mining entire worlds sounds fantastical, but within a Type 1 civilization's capabilities, large-scale automated mining and manufacturing could make it possible. Swarms of robotic assemblers could harvest metals from asteroid belts, refining and shaping them in orbit, never having to lift material from the deep gravity well of a planet. Another challenge is control. Thousands or millions of collectors must maintain stable orbits, avoid collisions, and keep their energy beams precisely aimed. This requires a level of automation and artificial intelligence beyond what we have now. Systems that can coordinate vast fleets without constant human oversight. Why attempt something so enormous? Because the payoff is just as enormous. With the energy of an entire star at its disposal, a civilization gains almost unimaginable power. Energy scarcity, a constraint that has shaped every society in history, simply disappears. With that energy, entire planets could be terraformed, their climates and ecosystems engineered at will. Space habitats, vast rotating colonies in orbit, could be built by the millions, each sustaining millions of inhabitants. Artificial worlds could be lit and warmed in the cold reaches of the outer solar system. It also opens the door to staggering feats of computation. Vast data centers, powered by a star's full output, could simulate entire worlds, perhaps even whole universes, in exquisite detail. A Type 2 civilization could host consciousness itself in digital form, creating billions of simulated realities for exploration, entertainment, or experimentation. Interestingly, Dyson's idea was motivated not only by speculation about our own future, but by the search for extraterrestrial intelligence. He realized that if advanced civilizations built such megastructures, they might be detectable from Earth. A Dyson swarm would block much of a star's visible light, but emit strongly in the infrared, a signature that telescopes could search for. In recent decades, astronomers have indeed looked for such signals. The most famous case was KIC 8462852, popularly known as Tabby's star, which displayed mysterious dimming patterns in its light. While the most likely explanations are natural, dust clouds or comet fragments, the possibility of artificial megastructures briefly captured the public's imagination. So far, we've found no confirmed Dyson swarms, but the search continues. Building a Dyson swarm is not just a technical challenge. It is a cultural one. It would require long-term planning on timescales of centuries, possibly millennia. No single generation would see the work completed. This demands a civilization with stability, patience, and the ability to sustain ambitious projects far beyond individual lifespans. It also requires a unity of purpose. A Dyson swarm is not a weapon or a tool for a single nation. It is an infrastructure project for an entire species. That implies a level of global governance and cooperation that even a Type 1 civilization would need to refine. The Dyson concept is only one path to Type 2. Some thinkers have imagined stellar engines, massive structures that not only harvest a star's energy, but use it to move the star itself, towing entire solar systems through the galaxy. Others envision creating artificial stars, controlled fusion reactors the size of moons, to serve as portable suns for interstellar colonies. Yet for all these visions, the Dyson swarm remains the most iconic. It is a symbol of ambition, of taking the next step beyond a single world to embrace the full power of a star. And here's the strange thing. While such a project seems like science fiction, it follows directly from our current trajectory. Humanity already collects solar energy from orbiting satellites, and our robotic explorers already mine and manipulate objects in space. Scale those efforts up by a factor of millions, and you are well on your way to surrounding the sun. We may be centuries away, but in cosmic terms, that's only an instant. If we endure long enough to become a true Type Y civilization, the path to Type 2 will open before us. A path lined with solar collectors, artificial worlds, and the light of a star gathered into the hands of its children. In the next chapter, we'll go further still, past even the mastery of a single star, into the realm of civilizations that command entire galaxies, shaping their light, their matter, and perhaps even the fabric of space itself. That is the territory of the Type 3 civilization, and it is where human imagination must stretch to its furthest limits. Chapter 3: Masters of the Galaxy. If a Type 2 civilization commands the energy of its home star, a Type 3 civilization commands the energy of hundreds of billions of stars, the full output of an entire galaxy. This is a scale so vast that it transforms our sense of what civilization even means. A society spanning a galaxy would not simply be a larger version of what we know. It would be something fundamentally different, a network of minds, machines, and worlds woven together across distances so great that light itself would take tens of thousands of years to travel between them. To imagine this, picture the Milky Way, a flat, spiral disk 100,000 light years across, containing perhaps 200 to 400 billion stars, each with its own planets, moons, asteroids, and comets. Between them are clouds of gas, dark matter halos, and the immense black hole at the galactic center. A Type 3 civilization would not merely visit these stars, it would shape them, harvest them, and coordinate their energy flows. Entire star systems could be surrounded by Dyson swarms or other megastructures, their combined output beamed across the galaxy. The civilization might use stellar energy for computation on an unimaginable scale, creating galactic internets where information flows in streams of light and gravitation itself is manipulated to transmit data faster than conventional physics allows. The first challenge is travel. To cross even part of the galaxy, a civilization must develop propulsion far beyond chemical rockets or even nuclear fusion drives. Possibilities include light sails powered by focused beams from giant lasers, antimatter engines, or even speculative technologies like warp drives or wormhole networks, methods that might bend or bypass space-time itself. Expansion might not be carried out by crewed ships at all, but by swarms of self-replicating probes. These von Neumann machines could land on asteroids or moons, mine materials, and build copies of themselves. Each new probe would fly to another star, repeating the process. In theory, such machines could fill a galaxy in a few million years, a blink compared to the galaxy's age. Once spread across the galaxy, a Type 3 civilization would have to knit itself together. At this scale, instantaneous communication may be impossible without new physics, so the civilization might not be a single centralized government, but a vast federation, or even a loose ecosystem of cultures and entities, each adapted to its local star systems, but connected by shared heritage and knowledge. Energy storage and transmission would be reimagined entirely. Gigantic stellar grids could route power between systems, balancing surpluses and deficits as stars age and fade. Some stars might be moved into optimal positions for energy harvesting, or even merged to extend their lifespans. Black holes could be harnessed as ultimate power plants, their gravitational forces driving energy extraction at nearly perfect efficiency. With control of so much energy, a Type 3 civilization might go beyond simply using the galaxy. It might reshape it. Stars could be rearranged into new patterns for stability or aesthetics. Planets could be moved into habitable zones or built from scratch using mined material. Entire regions of space could be enclosed in galactic-scale habitats, turning star clusters into artificial environments. More speculative still, Such a civilization could experiment with cosmic engineering, altering the very structure of the galaxy's spiral arms, stabilizing its central black hole, or influencing the orbits of dark matter itself. At this stage, the boundary between civilization and natural law begins to blur. But in becoming so vast, does a civilization remain one civilization? Or does it fragment into countless different societies, each shaped by its environment, evolving along its own path until the original identity is almost forgotten? In human terms, think of how cultures diverge after only centuries of separation. Across thousands of light years and millions of years, differences could become profound. It's possible that a Type 3 civilization might be more like a galactic ecology than a single political entity, a web of interacting species, cultures, and intelligences, some biological, some artificial, all drawing from the galaxy's energy pool, but pursuing wildly different goals. If such civilizations exist, how would we know? Astronomers like Carl Sagan have suggested that Type 3 civilizations might be detectable through waste heat on a galactic scale. A galaxy filled with Dyson swarms, for example, would shine less brightly in visible light and more strongly in the infrared. So far, surveys have found no convincing examples. Most galaxies we see behave like natural systems, with no large-scale infrared excess that can't be explained by dust and star formation. But our search is still in its infancy, and the galaxy is vast. If Type 3 civilizations are rare, they may lie far beyond our current reach. Or they may camouflage themselves, blending into the cosmic background for reasons we cannot guess. A final question haunts the Type 3 vision. Can a civilization survive long enough to reach it? The greater the scale, the greater the potential for catastrophe, whether through internal conflict, technological miscalculation, or external cosmic hazards like gamma-ray bursts. Sustaining a civilization across billions of stars may require a level of stability, wisdom, and adaptability that is as rare as the engineering feats themselves. But if it can be done, the rewards are beyond anything we can presently imagine. A Type 3 civilization would be, for all practical purposes, immortal on the galactic stage, capable of enduring for eons, guiding the fates of stars themselves, and perhaps even preparing to take the next step beyond the galaxy into the realm of the universe as a whole. In the next chapter, we'll look at that step, the hypothetical Type 4 civilization, and what it might mean to wield the energy of the entire cosmos. Here, speculation meets the edge of physics, and the possible begins to blend with the truly incomprehensible. Chapter 4: Architects of the Universe. Beyond the scale of galaxies lies a realm so immense that even the most ambitious human dreams barely graze its surface. This is the domain of the Type 4 civilization, a society capable of commanding the energy of the entire observable universe. If the leap from Type 2 to Type 3 is daunting, the leap from Type 3 to Type 4 is staggering. Here we are no longer speaking of billions of stars, but of hundreds of billions of galaxies, each containing its own billions of stars and planets. We are talking about harnessing energy on a scale that rivals the very output of the cosmos itself. The Milky Way is vast to us, but it is just one island among countless others in the cosmic ocean. In the observable universe, there may be 2 trillion galaxies, scattered across 93 billion light-years of space. Each of these galaxies, in turn, contains staggering amounts of matter, energy, and, if the universe is as fertile as some believe, the potential for life and intelligence. A Type 4 civilization would somehow link these galactic domains into a single, coherent system. That means communication and travel across intergalactic distances, which are far greater than anything in a single galaxy. Even traveling at the speed of light, a signal from the Milky Way to the Andromeda Galaxy, our closest large neighbor, would take over 2 million years to arrive. To function at this scale, a Type 4 civilization would likely need to move beyond conventional physics as we understand it. Wormholes, hypothetical shortcuts through space-time, might be engineered to link galaxies directly. Artificial control over the fabric of space-time itself could allow for near-instant travel and communication, turning the universe into a navigable network rather than a scattering of unreachable points. The energy demands for such feats are incomprehensible in human terms. But to a civilization already harnessing the light of billions of stars, even the energy output of a galaxy might be just the starting point. A Type 4 civilization could reshape the architecture of the cosmos. They might accelerate the formation of new stars by compressing gas clouds, extend the lifespans of existing stars, or move entire galaxies into optimal positions for long-term stability. At the extreme, they might engage in black hole engineering, using the rotational energy of supermassive black holes to power unimaginable machines, or even creating artificial black holes to serve as power plants, data storage centers, or gateways through space-time. They could manipulate dark matter and dark energy, the mysterious components that make up about 95% of the universe's mass energy content. This would open possibilities we can barely articulate, perhaps even altering the ultimate fate of the universe itself. Why would a civilization need such power? One reason might be survival. Stars burn out, galaxies drift apart, and the universe is not eternal in its current form. In trillions of years, even a Type 3 civilization's power sources will fade. A Type 4 society might take steps to slow, reverse, or outmaneuver this cosmic decay, moving into new universes if the opportunity exists, or creating artificial universes of their own. If Type 4 civilizations are possible, their absence becomes even more puzzling. The Fermi paradox, the question of where is everybody, becomes sharper. At this level of capability, a civilization's presence could leave unmistakable signatures, altered galactic structures, coordinated patterns of light across billions of light years, or even the manipulation of the cosmic microwave background. And yet, we see none of this. Are such civilizations impossible? Do they self-destruct before reaching this stage? Or is it that their activities are hidden, subtle, or fundamentally unlike anything we expect? Here we touch the edge of human thought. We are trying to envision a society so advanced that our own existence might be as irrelevant to them as the behavior of atoms is to us. Their civilization might not be composed of individuals at all, but of vast unified intelligences, minds spanning entire superclusters, thinking on timescales of millions of years. It is even possible that a Type 4 civilization would no longer inhabit physical space in any way we understand. They might live as pure information in a computational substrate woven into the fabric of the universe, or in dimensions beyond the ones we perceive. If the universe has a finite lifespan, even a Type 4 civilization must face the ultimate challenge: how to persist beyond the end. This might mean escaping into a new cosmos through some kind of cosmic tunneling, or initiating a baby universe in which life and intelligence can continue. From our perspective, these are only shadows of possibilities, but the fact that we can imagine them at all is telling. It means that even from our tiny perch on a small planet, we can glimpse, however faintly, the ladder's highest rungs. In the next chapter, we'll explore an even more speculative idea: the Type 5 civilization, one that not only spans universes, but masters the multiverse itself. Here, the questions become not only about engineering and survival, but about meaning, consciousness, and what it is to exist when everything is within reach. Chapter 5: The Lords of the Multiverse. Beyond the staggering reach of a Type 4 civilization lies a concept so speculative, so far beyond the edge of confirmed science, that it reads like mythology: the Type 5 civilization. If a Type 4 commands the energy of the entire observable universe, a Type 5 commands the energy of all universes, the entirety of the multiverse, if such a thing exists. This is the point where physics, philosophy, and imagination merge. We are no longer talking about a single space-time continuum, but an infinite or near-infinite set of them, each with its own laws of physics, constants, dimensions, and possibilities. Some might be eerily similar to ours. Others could be utterly alien, with no matter, no light, perhaps even no time as we understand it. The idea of the multiverse comes from several different branches of science and speculation. In cosmology, some theories of cosmic inflation suggest that our universe is just one bubble in a vast foam of universes, each forming with its own parameters. In quantum mechanics, the many worlds interpretation posits that every possible quantum outcome actually happens, creating an ever-branching tree of realities. And in string theory, higher dimensional spaces, brains, could give rise to multiple universes stacked or drifting within a greater dimensional arena. If any of these scenarios are true, the total reality is far larger than the observable cosmos, and within that greater reality, a sufficiently advanced civilization might find ways to move between universes, harvest their resources, and perhaps even create new ones. For a Type 4 civilization, the laws of physics in their home universe are a given. For a Type 5, those laws become just one set among many. Moving between universes could require engineering not just matter and energy, but the very constants of reality. bending the speed of light, altering the strength of gravity, or rearranging the quantum fields that define existence. They might build cosmic gateways in the high-energy environments near black holes, or use controlled Big Bang events to seed entirely new universes. In this vision, the multiverse becomes a navigable landscape, one where a civilization can chart courses from one cosmic bubble to another like sailors crossing an ocean of creation. The energy resources available at this scale are effectively limitless. A Type 5 civilization could tap the total mass energy of countless universes, each containing galaxies, stars, and exotic structures unknown to us. They could draw from phenomena outside our own physics, forms of matter or energy we cannot even name because they do not exist here. Such resources would make any problem of scarcity vanish entirely. In fact, the challenge for a Type 5 might not be finding energy, but managing and directing it without collapsing or destabilizing the universes in which they operate. A Type 5 civilization would not be limited to a single physical form or even a single kind of existence. Minds could be embodied or disembodied, biological or artificial, individual or collective. Some might exist as pure patterns in quantum fields, others as hyperdimensional structures spanning entire universes. Communication could occur instantly across distances that would take light eons to cross in our universe, by exploiting the metastructure of the multiverse itself. To us, such beings might appear omniscient and omnipresent, able to reach into our universe at will, influencing events in ways that seem like miracles. The question then becomes, what would a civilization do with such power? In a multiverse, there may be infinite versions of every event, every person, every choice. Would a Type 5 civilization seek to explore them all, to catalogue and understand them, or to guide them towards some purpose, perhaps the survival and flourishing of life across all realities? Some philosophers have speculated that such civilizations might adopt roles resembling what ancient humans would call gods, creators, caretakers, or destroyers of worlds. They might seed life in universes where it would otherwise never arise, or adjust the constants of reality to favor complexity and intelligence. Others might choose to remain unseen, letting each universe evolve according to its own path. With infinite reach comes infinite responsibility. Altering one universe could have cascading effects on others, especially if the multiverse is interconnected in ways we do not yet understand. A Type 5 civilization would need an ethical framework vast enough to account for countless realities, each with its own forms of life and intelligence. Would they intervene to prevent suffering? Would they allow hardship and struggle to shape the growth of civilizations, as it has shaped ours? These questions are not just about morality. They are about the role of intelligence in the structure of reality itself. The Fermi paradox takes on a new dimension here. If Type 5 civilizations exist, why have we never detected them? Perhaps they are so far beyond us that we cannot recognize their actions. Or perhaps they choose not to reveal themselves, either to avoid influencing younger civilizations, or because our universe is one of countless others they tend. And our story is only a small note in a far greater symphony. There is also the possibility that universes with the right conditions for life are rare, and that even in a multiverse, civilizations of any type are vanishingly scarce. In that case, a Type 5 might wander for eons between the rare pockets of life, becoming more like cosmic archivists than empire builders. The ultimate challenge for any civilization, even one with infinite resources, is the eventual fate of reality. If the multiverse itself has a beginning and an end, then even Type 5 civilizations must face the question of what lies beyond. Some theories suggest that universes can spawn new universes endlessly, like branches sprouting from a tree without end. Others imply that the multiverse is finite, and that once all possible universes have run their course, there is truly nothing beyond. If the latter is true, a Type 5 civilization might seek to escape even the multiverse into a domain outside of time, space, and causality itself. In doing so, they would pass beyond the Kardashev scale entirely, into a realm where words like civilization or energy no longer have meaning. From our current standpoint, a young, fragile, planetary species, the Type 5 civilization feels impossibly remote. Yet the very fact that we can imagine it means that it is at least conceivable within the framework of our thought. Every great human achievement began as a vision beyond the present, and this is simply that vision extended to its furthest limit. Perhaps no civilization ever reaches this stage, or perhaps some do, and from their vantage point, they watch the young species of the cosmos struggle upward, knowing that the first rung of the ladder, harnessing the energy of a single world, is the hardest to climb. In the next chapter, we'll leave the pure speculation of the multiverse and turn to something closer to home, the practical and philosophical challenges of humanity's next steps. For if we ever hope to take even the smallest stride toward the Kardashev ladder's higher rungs, we must first decide not just how to climb, but why. Chapter 6. The First Rung. Every great ascent begins at the ground. For humanity, that ground is here, on a small blue world orbiting an ordinary star, where the light of the sun falls freely and the air hums with the life that made us. It is easy to look up the Kardashev ladder and be intoxicated by visions of Dyson spheres, galactic networks, and multiversal gateways. But the truth is that the first step may be the hardest of all. Reaching Type 1 means mastering not only the energy of an entire planet, but also the cooperation, foresight, and restraint required to use it wisely. Our current civilization is a paradox. On one hand, we have already changed the face of our world in ways no other species has, splitting atoms for power, creating vast electrical grids, and sending our machines beyond the reach of the sun's gravity. On the other, we remain dependent on fuels laid down hundreds of millions of years ago, burning them in ways that poison our atmosphere and destabilize the climate that has nurtured us. We wield fire like a child playing with a torch in a library, clever enough to make the flame but not wise enough to keep it from spreading. To truly become a planetary civilization, we must learn to capture and store the energy that falls upon us every day, in amounts far beyond our needs. The sunlight that reaches Earth in a single hour is more than humanity consumes in an entire year. It pours across deserts, sparkles on oceans, and blazes from the sky above every city, yet we gather only a fraction of it. The winds, the tides, the slow rumble of the Earth's molten heart. These too are power sources waiting to be tapped with greater efficiency and care. But energy is only part of the story. The harder task is creating a system that can sustain itself without collapsing under its own complexity. This means developing technologies that do not simply extract from the environment, but exist in balance with it. It means redesigning cities to use energy as efficiently as possible, creating global grids that share power seamlessly, and building storage systems that smooth the peaks and troughs of supply and demand. Above all, it means making these systems resilient, able to survive storms, disasters, and the shifting needs of a changing world. Reaching Type 1 will also demand something we have rarely achieved: true global coordination. Energy on a planetary scale cannot be the private possession of a few nations without creating instability. A blackout in one region could ripple through the entire system. Decisions about energy use would affect billions of lives simultaneously. This calls for governance structures capable of making decisions that reach beyond borders, guided by a shared recognition that we are not merely citizens of countries, but of a single, interconnected planet. There is also a cultural dimension to the climb. As our reach expands, so too must our sense of responsibility. Type 1 status is not just about engineering achievements. It is about developing a planetary identity, an understanding that our survival depends on the health of the whole system. Wars fought over resources, mistrust between nations, and exploitation of the vulnerable all undermine the stability needed to maintain such a civilization. Without unity, the infrastructure we build will become brittle, and the higher we climb, the harder we will fall. It is tempting to imagine that the technologies themselves will save us. Fusion reactors, advanced solar collectors, global AI-managed grids. These may indeed be part of the solution, but they will not erase the need for cooperation and foresight. In fact, the more powerful our tools become, the greater the consequences of using them unwisely. A mismanaged planetary grid could plunge the world into darkness. A poorly designed climate intervention could tip the balance into disaster. The first rung of the Kardashev ladder is not simply about having the power, but proving we can wield it without losing our balance. Some thinkers have argued that the very process of reaching Type 1 will change us fundamentally. The problems we will face, climate change, resource distribution, population pressures, cannot be solved in isolation. They will force new levels of coordination and empathy, binding humanity into a web of mutual dependence. The same network that transmits energy will transmit information, culture, and ideas, weaving together a planetary consciousness. If we succeed, the boundary between us and them may blur until the idea of a single human family is not a dream, but an everyday reality. Others warn that this transformation is not inevitable. The same technologies that could unite us could also divide us further. If access to planetary scale energy is unequal, it could create a new kind of stratification, not between rich and poor nations, but between those with control over the energy grid and those without. History suggests that without conscious effort, the benefits of new technologies often flow first to the few and only slowly to the many. The leap to Type 1 will require deliberate choices to ensure that the energy of the planet is a common inheritance, not a prize hoarded by the powerful. Standing here at this moment in history, we are poised between two futures. In one, we fail to make the transition. Our energy systems collapse under the strain of conflict and environmental damage. Civilization fragments, and the Kardashev ladder becomes nothing more than a story we once told ourselves. In the other, we take the step with care and vision, building a world where energy flows as freely and sustainably as water in a river, and where our technologies extend not just our power, but our wisdom. The first rung is the proving ground. It will determine whether we are capable of the patience and unity required to climb further. For a Type 1 civilization, the planet is not a battlefield or a mine to be stripped bare. It is a home to be tended, a foundation upon which we can build our future in the stars. If we cannot keep that foundation intact, there will be no ladder to climb. The journey to the higher rungs begins here, in the choices we make now. We are still a Type 0 civilization, but we are learning, experimenting, and imagining. And sometimes, in quiet moments, when we look up at the night sky and see the stars, not just as points of light, but as destinations, we glimpse the truth. The first step is the hardest, but it is also the one that carries us across the threshold from surviving to truly living as a species that belongs to the cosmos. In the next chapter, we will look at the psychological dimension of this transition, how the dreams, fears, and mythologies of humanity shape the way we imagine our future, and how those stories might influence whether we ever reach the stars at all. Chapter 7. The stories we tell about tomorrow. Long before anyone spoke of Kardashev scales or Dyson swarms, humanity told stories about the future. Around campfires and in echoing halls, we imagined golden ages where peace and prosperity reigned, or dark ages where the world fell into ruin. These tales were our first simulations, our earliest attempts to model what might come next. They carried lessons, warnings, and aspirations, even when they wore the clothes of myth. And though our technologies have changed, the instinct to imagine tomorrow has never left us. Every civilization we know of has created its own vision of what lies ahead. Sometimes these visions are hopeful: cities in the clouds, ships crossing the stars, abundance for all. Sometimes they are fearful: skies blackened with smoke, machines turning against their makers, worlds stripped bare. The way we picture the future shapes the paths we are willing to take toward it. A culture that dreams of paradise may work toward building it. A culture that fears collapse may cling so tightly to the present that it brings about the very decline it dreads. In the modern era, These visions have become sharper, painted in the details of science and engineering. The idea of interstellar travel, once the realm of mythic chariots and winged horses, now appears as engines and starships, backed by equations. Artificial intelligence, once imagined as magical talking statues, now flickers in glowing screens and responds to human voices. We live in a time when speculation about the far future often feels only a short leap from reality, and that closeness changes the way we respond to it. Optimistic visions have a powerful pull. They tell us that progress is possible, that human ingenuity can solve the challenges of energy, climate, and cooperation. In these futures, our descendants may live in harmony with the planet, or spread among the stars, carrying the memory of Earth into every new world they inhabit. Such stories inspire innovation. They make it easier to imagine spending decades or centuries on projects whose results we may never see. They turn the climb up the Kardashev ladder into a quest worth undertaking. But optimism alone is not enough. Pessimistic visions serve their purpose too. They remind us of what's at stake if we fail to act. Stories of worlds gone wrong, seas risen to swallow cities, skies choked with dust, societies collapsing under their own weight, may be bleak, but they can stir us to avoid the mistakes they portray. In a strange way, dystopias can be fuel for hope, showing us the paths we must not take. The challenge is balance. A culture that dwells only on utopias may become blind to danger, assuming that progress is inevitable. A culture trapped in dystopia may lose the will to try at all. Both extremes can be paralyzing. What we need is a vision that acknowledges both possibility and peril, that says, yes, we can climb higher, but it will take care, discipline, and the humility to learn from the past. Our visions of the future also carry deep cultural fingerprints. Different societies emphasize different priorities: technological mastery, spiritual growth, social harmony, or personal freedom. A civilization's stories about its future reveal what it values most in the present. For some, the dream is a world of perfect equality. For others, it is boundless exploration. For some, the future is a return to a simpler way of life. For others, it is the embrace of complexity and speed. And then there is the personal element. Each of us, whether we realize it or not, carries a private vision of the future. For ourselves, for our families, for the world. These personal visions add up to the collective vision of our species. If enough people believe that humanity will survive and thrive, they will work in ways that make it more likely. If enough believe we are doomed, they may act as though there is nothing to save. The first steps toward becoming a Type 1 civilization will not be built only in laboratories and factories. They will be built in imaginations. We must be able to picture what a planetary civilization looks like, not just in terms of power grids and spaceports, but in how it feels to live in such a world. Will children grow up seeing Earth as a single shared home? Will leaders make decisions with centuries in mind? Will technology be a tool for all, rather than a weapon for the few? This is why art, literature, and storytelling matter as much to the future as engineering and policy. They are the testing grounds for our ambitions, the places where we can try on possibilities without the cost of reality. A novel about life in a space habitat can spark a career in aerospace engineering. A film about a global environmental collapse can ignite movements for sustainability. The stories we tell are the seeds from which our realities grow. Yet stories alone cannot guarantee a good outcome. They must be paired with the will to act and with systems capable of turning vision into reality. A world where everyone dreams of the stars, but no one builds rockets will never leave the ground. A society that warns of climate change in its art, but does nothing in its policy, will still see the seas rise. The bridge from imagination to achievement is built from both inspiration and effort. As we stand here, still far from even the first rung of the Kardashev ladder, we should remember that the climb is not just technical, it is psychological. Our tools will only take us as far as our minds can envision. The future belongs to those who can dream of it clearly enough to build it, and who can face its risks without losing heart. In the next chapter, we will explore the paradox of power. How every leap forward in energy and capability also brings new dangers, and how the same technologies that could carry us to the stars might also hasten our fall if we are not ready to use them wisely. Chapter 8. The Paradox of Power. Every step up the Kardashev ladder is a step into greater capability and greater risk. The same technologies that can lift a civilization to new heights can also be the ones that bring it crashing down. Power, in the cosmic sense, is indifferent. It will amplify whatever we are, for better or for worse. A society that is wise will use it to build, to sustain, and to explore. A society that is reckless will find that power only makes its destruction swifter. This paradox is as old as humanity itself. Fire warmed our shelters and cooked our food, but it also burned our homes. Metallurgy gave us plows and architecture, but it also gave us swords and cannons. Nuclear energy offers almost limitless electricity and the promise of interstellar propulsion. Yet it also brought the shadow of annihilation in the form of weapons that could end civilization in an afternoon. Each leap forward carries both gift and curse. As we approach the threshold of Type 1, our tools are becoming more intricate and interconnected. Global energy grids promise abundant power, but a failure in such a system could cascade across continents. Artificial intelligence could coordinate planetary scale projects, but poorly designed AI could act unpredictably, even destructively, in ways we cannot contain. Climate engineering might stabilize the planet's atmosphere, but a miscalculation could disrupt weather patterns for generations. The paradox grows sharper as we imagine higher levels. A Type 2 civilization capable of harnessing the energy of an entire star would have the ability to terraform worlds, but also to sterilize them. A Type 3 commanding galactic energy flows could seed life throughout the stars, or wipe out entire systems in acts of war or accident. At the heights of Type 4 and Vi, the very fabric of space-time becomes a tool. and a single error might ripple across universes. The real challenge is not acquiring power, but mastering restraint. In history, civilizations that could not balance their ambition with caution often collapsed under their own weight. This is why the climb up the ladder is not just a technological progression, but a moral one. A species must learn to hold power without being consumed by it. Without this, each new rung is only a more dangerous perch from which to fall. Restraint does not mean stagnation. It means building systems of governance, oversight, and ethics that can keep pace with technological growth. It means ensuring that no single group can monopolize power to the point of destabilizing the whole. It means designing technologies with fail-safes, redundancies, and ways to correct mistakes before they spiral out of control. Above all, it means fostering a culture that values foresight over short-term gain and responsibility over conquest. There is a danger in thinking that these problems will solve themselves as we advance. Intelligence and wisdom are not the same thing. A civilization can be brilliant, innovative, and immensely capable, yet still blind to the long-term consequences of its actions. The faster we climb, the more critical it becomes to look not just at the next rung, but at the entire ladder and the ground far below. The paradox of power is also the paradox of trust. On a planetary scale, no single nation can prevent catastrophe alone. Trust between nations, between cultures, and between generations becomes the foundation of survival. Without trust, every advance becomes a potential weapon, and suspicion can make cooperation impossible. But trust is fragile, and history shows how quickly it can be broken. The climb requires not just building machines, but building confidence that they will be used for the benefit of all. And yet, despite the risks, we continue to reach higher. There is something in us, a restlessness, a hunger for more, that drives us forward. The challenge is to channel that drive into creation rather than destruction, to ensure that the story of humanity is one of ascent, not collapse. This is the tightrope we walk. Too little ambition, and we remain bound to one fragile world. Too much without caution, and we risk losing everything. As we move forward, the paradox will never vanish. It will be with us at every stage, in every technology, in every decision about how to use what we have gained. The difference between a civilization that endures and one that falls may come down to how seriously it takes that paradox, whether it sees power as a tool to be wielded with humility or a prize to be taken without thought for the cost. In the next chapter, we will explore the role of cooperation in survival, how unity at scales we have never before achieved will be the key to stepping beyond our home world and ensuring that the climb up the ladder does not end with us. Chapter 9. The Web of Unity. If there is a single thread that holds together every vision of an advanced civilization, it is cooperation. Without it, the climb to the next rung of the Kardashev ladder becomes impossible. The energies we seek to control are vast. The projects we dream of are measured in centuries, and the challenges we face, from climate change to asteroid defense, are indifferent to national borders. A divided species cannot build a planetary civilization. Cooperation is not a natural default for humanity. Our history is filled with rivalry, competition, and conflict, often over the very resources we now hope to manage collectively. But it is also filled with moments when we have set aside differences to achieve something greater. The construction of the International Space Station, the eradication of smallpox, the global scientific collaborations on climate research. These are reminders that we are capable of acting as one when the stakes are clear and the benefits are shared. The scale of unity required for Type 1 status is unlike anything we have yet achieved. Imagine an energy grid that spans the globe, drawing on the sun, the wind, the tides, and geothermal heat, balancing loads from continent to continent. Such a system would require trust, that power will be shared fairly, that no region will be deliberately left in darkness for political advantage. It would require agreements on maintenance, protection from sabotage, and protocols for repair in the event of disaster. Beyond energy, unity must extend to knowledge. The breakthroughs that will carry us forward in fusion power, in space propulsion, in planetary defense, must be shared openly enough to benefit all of humanity, yet safeguarded against misuse. This balance between openness and security is delicate. Share too little and progress slows. Share too much without safeguards, and the same knowledge that could build a better world could also tear it apart. Cooperation also means thinking beyond the present. Our political systems are often built around short election cycles, but planetary projects will take decades, even centuries, to bear fruit. The seeds we plant today, in infrastructure, in environmental restoration, in education, may not fully bloom until long after we are gone. To cooperate at the planetary level means to trust not only our current partners, but also generations yet unborn. It means creating institutions that can endure, adapt, and remain stable even as cultures and leaders change. There is another dimension to unity that is less tangible but no less important: identity. We must begin to see ourselves as members of a single human civilization, not merely as citizens of one nation or one culture. This does not mean erasing differences. Diversity of thought, tradition, and perspective is a strength. But it does mean holding a shared understanding that the survival and flourishing of our species comes first. When an asteroid is on course to strike Earth, it will not matter what languages we speak or which flags we fly. When the planet warms beyond a critical point, no border will hold back the consequences. Achieving this identity may require a shift in how we tell our own story. For much of history, we have told it in fragments. The history of nations, the rise and fall of empires, the victories and defeats of particular peoples. A planetary civilization will need a planetary narrative, one that places all of humanity in the same arc. In such a story, the moon landing is not just an American triumph, but a human one. The discovery of a life-saving vaccine is not the achievement of one laboratory, but of the species as a whole. Technology can help weave this web of unity. Global communication networks already allow a conversation between two strangers on opposite sides of the world to happen in real time. Shared projects in space exploration, environmental monitoring, and scientific research can create a sense of common purpose. But technology alone cannot create trust. That must be earned through fairness, transparency, and the consistent choice to act in the interest of all. The danger is that unity might only come in response to crisis. History suggests that large-scale cooperation often emerges when there is an immediate visible threat, an invading army, a spreading disease, a looming famine. But the climb up the Kardashev ladder will require cooperation even in times of peace, when the threats are distant or abstract. We will have to learn to act together, not just to avert disaster, but to build a future worth having. The web of unity will not be perfect. It will fray, it will strain under disagreement, and it will require constant repair. But without it, our climb ends here. With it, we will have the foundation to spread beyond our home world, to carry our shared story into the stars. In the next chapter, we will turn to the question of time, how civilizations that aim to shape centuries and millennia must rethink their relationship to the present, and how long-term vision may be the rarest and most essential resource of all. Chapter 10. The Long Horizon. To climb the Kardashev ladder is to step into a different relationship with time. For most of human history, our plans have spanned years, perhaps decades. Empires rose and fell in centuries, but the lives of individuals and the rhythms of communities were measured in seasons. A farmer planted in the spring and harvested in the fall. A ruler planned for the next war or the next succession, not for the state of the world in 1,000 years. A planetary or interstellar civilization cannot afford such short horizons. The projects required to reach and maintain each rung are vast. Solar collectors in orbit, planetary defense systems, space habitats, generational starships, and many will not bear fruit for decades or centuries. The people who start them will never see them finished. The benefits may be enjoyed by descendants far removed from those who did the work, and the dangers of neglect may only emerge long after the original decision-makers are gone. To act effectively at this scale, a civilization must learn to think in deep time. This means measuring progress, not in immediate returns, but in the quiet accumulation of resilience, capability, and knowledge. It means planting seeds whose harvest will be gathered in centuries, and maintaining structures that must endure through generations. The cathedral builders of medieval Europe, who began projects knowing they would be completed by grandchildren they would never meet, offer a faint glimpse of the mindset required. Except now, the cathedral is the entire planet, and the work must continue for as long as the species endures. Thinking in deep time also means accepting that the world will change in ways we cannot fully predict. The people of the future will live with different technologies, values, and challenges than we do. To plan for them is to build flexibility into everything we create, to avoid locking them into decisions that may no longer make sense centuries from now. A global energy grid must be upgradable. A space habitat must adapt to changing needs. A planetary archive must survive not just in its original form, but in whatever formats future minds can understand. The difficulty is that our present systems of governance and economy are built for the short term. Political leaders are judged on what they accomplish in a handful of years. Companies are pressured to deliver profits each quarter. Individuals make choices within the span of a human lifetime. The incentive to invest in projects that will not mature for a century is weak, even when those projects are essential for survival. Overcoming this short-term bias may be one of the greatest challenges to reaching higher Kardashev levels. It will require new cultural values that reward long-term stewardship as much as immediate innovation. It may require new forms of governance designed to protect the interests of future generations. Councils or institutions that exist solely to guard long-term projects from the turbulence of politics and markets. Some thinkers have proposed that humanity should adopt future trustees, people or groups, tasked with representing those who are not yet born in decisions made today. In a civilization that thinks in deep time, the concept of legacy changes. Personal achievements become less about immediate recognition and more about contributing to a chain of effort that extends beyond one's lifetime. A scientist who begins research that will not be completed for 200 years still finds purpose in being part of the continuum. An engineer who lays the foundation for an orbital power station may die before it is operational, yet knows that without their work, it would never be built. This shift in perspective may also change how we view ourselves in the grand cosmic story. If we truly think in terms of millennia, then our time on Earth is not the final stage of humanity, but only the beginning. We become not the culmination of history, but the ancestors of civilizations yet unimagined. Every decision we make, every forest preserved, every atmosphere stabilized, every technology developed responsibly, is a message to them saying, "We were thinking of you." Yet there is a paradox here as well. The longer the time frame, the more uncertain the outcome. It is possible to work for centuries toward a goal, only to see it undone in a moment by war, disaster, or negligence. Deep time planning must be coupled with resilience, the ability to adapt when the unexpected happens, to rebuild when the long arc of intention is interrupted by sudden catastrophe. The long horizon is not simply about patience, it is about persistence. It is the commitment to keep climbing even when the top is far beyond sight, to keep building even when the benefits will come to people we will never meet. It is a form of faith, not in the supernatural, but in the idea that humanity can endure, and that our future is worth the work required to reach it. If we can cultivate this perspective, then each rung of the Kardashev ladder becomes not a distant dream, but a step we are already taking. And perhaps, centuries from now, when our descendants look back from a time when the energy of worlds and stars flows through their hands as naturally as water through ours, they will see that the real leap was not the moment we harnessed the power of the sun or crossed to another star, but the moment we learn to think beyond our own lives and to act as though the future mattered. Now that we have climbed through these visions, from the first tentative steps of a planetary civilization to the unimaginable reach of multiversal architects, one question remains. Not just can we make this journey, but should we? In the final reflections, we will consider what the pursuit of such power might mean for our identity, our values, and the story we choose to tell about what it means to be human.